Okay, today we will begin a new chapter, and this new chapter will be about organometallic chemistry, which is an important subset of coordination chemistry. So first I would look at the definition of organometallic chemistry and discuss what organometallic chemistry actually is, and then give you a brief historical introduction into organometallic chemistry before we discuss special topics within organometallic chemistry. So let us answer the first question. How is organometallic chemistry defined? It's not working again. What is the definition? So when we have an organometallic compound, then we have a complex with bonding interactions between one or more carbon atoms of an organic group or molecule and a metal atom. So in a sense, we have direct interactions between a carbon atom and a metal atom. So that means that when we have an organic ligand, it is not enough. The organic ligand must attach to the metal so that there are direct interaction between the carbon atom of the ligand and the metal. So therefore, we need to distinguish between an organometallic complex and what is called a metal organic complex. So in a metal organic complex, we have also organic ligands, but the donor atoms are not carbon. So the organic ligand is bound through a different atom but carbon to the metal. So let's practice this by one example. So for instance, which of the following molecules are metal organic and organometallic compounds, respectively? Okay, so we have here tetramethyl-10 on the one side, and here we have tetramethoxy-10. So which of those are organometallic compounds and which are metal organic compounds? You may unmute yourself to answer the question.
The first one is a metal organic.
The first one is?
The organometallic compound.
Organometallic.
Because there is a metal carbon bond.
Correct. And the second one is a metal organic compound because, well, we also have methyl groups here, but these methyl groups are bound to oxygen, and the oxygen is then bound directly to the tin. So this is would be called a metal organic compound. Okay. Now let us have a quick look at the significance of organometallic compounds. So organometallic compounds are industrially very important. So there's a large production of organometallic compounds that can be directly applied to various applications. So for instance, we know that aluminum alcohols are produced at a scale of approximately 50,000 tons a year, and tin alcohols, for instance, are produced at a scale of approximately 35,000 tons per year. But even more important than the production of organometallic compounds is the production of other chemicals using organometallic compounds as catalysts. So many organic metallic compounds are very important catalytic applications for the production of other molecules. So in particular, polymers and many simple organic molecules as well. So for instance, polypropylene is produced by organometallic compounds that act as catalysts in the order of 17 million tons per year. Polyethylene is made using organometallic compounds as catalysts at a scale of 36 million tons per year. Very simple molecules like acetaldehyde are produced using organometallic compounds in the order of 2.2 million tons a year, and acetic acid is produced at the scale of 1 million tons per year using organometallic compounds as a catalyst. And for that reason, as part of this course, we will also later on look at the applications of organometallic compounds as a catalyst and how they actually work in order to produce commodity chemicals. Okay, but before we go to that, let us look briefly at the history of organometallic chemistry and how it has evolved to become the important field it is today. So it is believed that organometallic chemistry started in 1760 with the discovery of cacodyl and cacodyl oxide by Cardet. So this was actually an accidental discovery when Cardet was working on new inks, and he found that actually when he reacted arsenic compounds, arsenic oxide in particular, with potassium acetate, that then a mixture of very smelly compounds evolved, and we know these compounds today as cacodyl, and the structure is here, and cacodyl oxide. The difference between these is that here you have a direct arsenic bond, whereas here you have an arsenic oxygen arsenic bridge. You can use this reaction actually to identify arsenic. So for instance, if you suspect that your food is poisoned with arsenic, you can take a portion of your food, react it with potassium acetate, heat it, and if you find that there's a very strong garlic-like smell evolving, then that's an indication that arsenic is in the sample, because these compounds smell similar to garlic in an analytical laboratory. Therefore, this reaction is found in application. However, of course, arsenic is toxic, so smell experiments with arsenic are not particularly helpful. So therefore, these kind of analytical smell experiments are not practiced very much today anymore. Yeah, so actually the name of cacodyl oxide and cacodyl are derived from the Greek word kakadis, whereas kakadis just means bad smell. Okay, now another very important step in organometallic chemistry was the discovery of Zeisel by William Zeisel. And Zeisel is known as the first olefin complex, even though at the time of its discovery, it was not known that this is actually an olefin complex, because only elemental analysis was possible, but not detailed structural analysis using X-ray diffraction techniques. But Zeisel already prepared a compound with the composition NaPtCl3 C2H4 by just reacting hexachloroplatinate in ethanol. Apparently, the ethanol reacted in some mysterious way with the hexachloroplatinate to give a compound with this composition that contained here this C2H4 fragment. However, it was only determined much later on that this fragment here binds with the carbon atom directly to the platinum, and actually does so in a pretty unique way. So much later, in 1969, the structure of Zeise's salt was clarified by X-ray diffraction, and you see the structure here. So you see that this structure is actually derived from a square planar structure. You have here the platinum in the center. So these chloroligands surround the platinum in a planar fashion. You have near 90-degree angles between two chlorines and the platinum here, and then ethylene acts as a fourth ligand, whereby the ethylene binds side on to the metals of the ethylene unit, stands approximately perpendicular to the plane made of these three chlorine atoms. So essentially we have here ethylene and all of them binding side on to the platinum. So this is of course a very unusual way of binding. So the question is, how does it actually work? And you get a clue at this when you analyze the bond length. Okay, so now the platinum carbon bond lengths are 216 and 215 picometers respectively, and the carbon-carbon bond length is 144 picometers. Now, when you compare this with the carbon-carbon bond length of a free ethylene molecule, then you see that this bond length is in between that what we would expect for a carbon-carbon bond and a carbon-carbon single bond. Okay, in a free ethylene molecule, the bond length would be 134 picometers. So that indicates that the carbon-carbon bond is weakened with respect to bond order in upon the complexation, and that some of the bonding or the bond order that was formerly present in the ethylene molecule has been given up in expense of making bonds between the carbon and the platinum. So now how exactly would this work? And we can see this in this diagram here. So the second carbon-carbon bond in the ethylene as a pi bond. So we see here the pi orbitals. And these pi orbitals, they can interact with metal d orbitals in a sigma fashion. So in this sense, the pi orbitals act as a sigma donor, and some of the pi electrons are sigma donated into the metal orbital. So this way, electron density is being removed from the carbon-carbon double bond, which would explain why the carbon double bond is weaker, or it's weakened. So in addition to that, there's also the possibility to use the pi star orbital of the carbon-carbon double bond in a pi acceptor fashion. So these interbonding pi star orbitals have actually suitable symmetry to overlap with metal d orbitals in pi fashion. So now the pi star orbitals are being empty, but the d orbitals may actually contain electrons, and then these electrons are being donated, well, from the metal d orbital into the pi star orbitals. So when you fill electron density in an interbonding orbital, well, then that also reduces the bond order, and it's an additional explanation why the carbon-carbon double bond is weakened and why the bond order is in between 1 and 2 and not like in a free ethylene molecule, just 2. So salt was an important discovery and a milestone in the history of organometallic chemistry. Another one was discovery of the first carbonyl by Ludwig Mohn in 1890. So Ludwig Mohn prepared nickel carbonyl as the first carbonyl and in an astonishing reaction. So carbon monoxide can actually directly react with nickel metal under very mild conditions near room temperature to form nickel tetracarbonyl, which is a volatile liquid. And Ludwig Mohn did not only discover nickel carbonyl, he also prepared an industrial process based on this reaction that is today being used for nickel purification. And that is called the Mohn process. And it works the following way. You take impure nickel, and then the nickel in the impure nickel reacts selectively with carbon monoxide to form nickel tetracarbonyl. So at 50 to 60 degrees Celsius, the reaction proceeds and the nickel tetracarbonyl is being produced in a gaseous form. So this way you have gasified the nickel. And in the next step, you use the relative thermal instability of the nickel carbonyl to, well, set the nickel free as metal again. So at 220 to 250 degrees Celsius, you can decompose the nickel tetracarbonyl to form back nickel and carbon monoxide, and then that nickel is produced in a highly pure form because previously the nickel has reacted selectively with the carbon monoxide. So you see here, for instance, some nickel spheres that have been prepared through the Mohn process that is practiced today, actually, despite the very high toxicity of the nickel carbonyl. Okay, another very important step was the discovery of the first Grignard reagents that you probably all know from organic chemistry. So Grignard reagents are organometallic compounds that have a great number of applications in organic chemistry, and they are forming in an astonishing reaction discovered by Victor Grignard. So when you react magnesium metal with an alcohol halide in the presence of ether as a solvent, then near room temperature in an exothermic reaction, the magnesium inserts in the carbon halogen bond through a mechanism that is still not well understood, despite the reaction is meanwhile being more than 100 years old. So it's still somewhat a mystery how this reaction actually proceeds. It's absolutely non-obvious that it would happen at all. But anyhow, it happens, and it happens very reliably. So we can form these Grignard reagents. Here, and these Grignard reagents have a lot of applicability in organic chemistry, and that is because they can turn electrophile into nucleophile. So in this compound here, Rx, well, we have a delta plus here on the carbon and a delta minus on the halogen. That makes, well, this R here an electrophile, while here, and I just see that the Grignard reagent is actually incorrectly written. We have actually here have to place the magnesium in between R and X, so I need to correct that. We have, because the magnesium is now bound to the rest R, a delta minus on the carbon and a delta plus in the magnesium. So now our rest R reacts as a nucleophile. Okay. Then in 1917, the first lithium alcohols were prepared by Wilhelm Schlenk. He's also the inventor of the Schlenk line, which is widely used today, still in laboratories. So lithium alcohols are very air sensitive. They hydrolyze easily, and some also spontaneously oxidize. So they self-ignite in air, and therefore you have to handle them under strict inert gas conditions. And for that, Wilhelm Schlenk invented the Schlenk line. At least the graduate students of you have probably seen them. So with the help of Schlenk line, you can selectively evacuate a flask that may contain a lithium alcohol, and then fill the flask back with an inert gas. Okay, so you have here these two glass tubes, okay, which are interconnected by other glass tubes, whereby you have, well, for each interconnection, two valves here in this position and that position respectively. So now here at this outlet, you can attach your reaction flask. And now the top line can be, for instance, placed under vacuum, and the bottom line here is attached to an inert gas like nitrogen or argon. So that when you actually open this valve here, you actually evacuate a flask which is attached here. You can evacuate this flask, and then you can actually close this valve and open this valve. And by opening this valve, you can fill your flask then with nitrogen or argon, so that you can perform any desired reaction under nitrogen or argon. So lithium alcohols were also an important discovery, because lithium alcohols are also widely used in organometallic chemistry, because they are highly reactive, and the alcohol rest is a strong nucleophile. Okay, now all these were very important steps, but organometallic chemistry was actually not widely known and extensive field until 1951, in which the first metallocene, the ferrocene, was discovered, and after that the field of organometallic chemistry expanded very, very rapidly, and the first ferrocene synthesis is also widely accepted as the birth of the contemporary organometallic chemistry. So ferrocene was discovered by Thomas Keeley and Peter Pawson, and like often in science, their first synthesis was not intended. It was actually an accident, an accidental discovery by serendipity. So what did Thomas Keeley and Peter Pawson actually have in mind? They wanted to react this Grignard reagent here, this cyclopentadienyl magnesium bromide, in the presence of iron chloride, iron trichloride, in order to make this compound here. which has the name ferrocene. So they planned the reaction the following way. So this, the two cycler pentadieno, two cyclopentadimer units would actually produce two radicals of this kind here. And these radicals then would actually couple to form this molecule. And then this molecule here with iron trichloride would produce the ferrocene. However, this is not what happened. Instead of that, they found a reaction product, which was a orange-yellow powder, and they analyzed that reaction product by elemental analysis, and they found that, well, there was one iron atom and two cyclopentadieno units in it. And so they connected these building units based on what was known in bonding of organometallic compounds in this fashion, as you see here. So the iron atom would be bound by two electron, two center bonds to a single carbon atom of the two cyclopentadimer rings. But soon this structure was doubted because the product, this yellow powder here, showed properties that was conflicting with this structure. And what were these properties? First of all, that structure here is coordinatively unsaturated and has only 10 valence electrons by electron counting. We can again practice our electron counting skills a little bit here. So when we, for instance, apply the neutral atom method, the iron would have 8 electrons. Okay, would contribute 8. So the overall molecule is neutral. And then we would need to cleave the bonds homoleptically, and that means that each cyclopentadieno ring would contribute one electron each. In 8 plus 2, well, this gives 10. You could also use the oxidation state method. Then in this case, the iron would be an iron 2 plus, so it contributes 6 electrons. And then our cyclopentadieno rings would contribute 2 electrons each. But again, we would arrive at 10 electrons. So such a complex, which has 10 valence electrons, should be highly reactive because 10 electrons is much less than 18, violating the 18 electron rule. However, the complex was found to be quite stable. Okay? So we have a very high air stability. In this complex, it's inconsistent with the 10 electrons. In addition to that, we can sublime this complex without decomposition. The thermal stability is much higher than we would expect it. And also the reactivity of the cyclopentadieno rings is much smaller. So according to this structure, we should be able to hydrogenate the cyclopentadieno rings. But if you try the experiment, then you see that they are very unreactive, and it's very difficult to reduce the double bonds to form single bonds. And last but not least, also spectroscopic observation contradicted the structure here. When you take an NMR of that compound, then you actually find only one NMR signal in the hydrogen and 13 carbon NMR spectrum, even though you should see multiple according to this structure here. And you also see only one CH stretch vibration in the IR. Whereas you actually see multiple different ones according to this structure. So therefore, suspicion grows that this structure was wrong. But if the structure is wrong, what is then the right structure? And Ernst Otto Fischer at University of Munich and Jeffrey Wilkinson at Harvard University independently proposed a very different structure with a very different kind of bonding involved. So they said that we actually would not have hepta-1 interaction between the metal and the ligand, meaning that there is no interaction between the metal and only one carbon of the cyclopentadienyl ring. So instead, this CP ring would act as so-called pentahaptoligand, in which all 5 carbon atoms would be involved in the bonding with the metal. So that would be possible because the ligand would act as an aromatic cyclopentadienyl ligand, whereby the whereby the pi electrons in the cyclopentadienyl ligand would be donated into the metal d orbitals of the iron. And that would result then in a sandwich structure as shown here. So this structure was called the ferrocene structure, and the molecule accordingly was named the ferrocene because the pi electrons, the ene properties of the cyclopentadienyl ligand would be used in order to make the interactions with the iron. So this, of course, was a very bold proposal, but it would explain, of course, a number of things. It would explain why the compound is so stable, because when you count now the electrons, you actually will arrive at 18 electrons. So let us just do this using the oxidation state method in this case. So the iron would have again 8 electrons, but the oxidation state of the iron would be +2. So we would subtract 2 electrons. So we would need to assign all bonding electrons to the ligands. Okay. So therefore we would have a cyclopentadienyl anion as the ligand that would have 6 pi electrons. Okay, mixture of 2 of these ligands, we would have 2 times 6 pi electrons, and that would give overall 12 electrons. So now 8 plus 12, that exactly gives 18 and would explain the stability of the compound. Now, so now this structure is consistent and not inconsistent. So please cross out that in here. So that structure is consistent with stability and low reactivity according to the 18 electron rule. Okay. It's also consistent with spectroscopic observations. So according to this structure, indeed, we should only observe 1 NMR signal and only 1 CH stretch vibration. So finally, this structure was confirmed by crystal structure determination of using X-ray diffraction, which actually proved Fisher's and Workman theory, who won the Nobel Prize for their proposal of this structure. In a crystal structure, you can then directly see the atoms in electron density map, and the electron density map just confirmed that these proposed sandwich structure really was present, and this was the final proof that the sandwich type ferrocene molecule really existed, and that we actually have a completely different kind of bonding present, which was not seen before in other organometallic compounds. So let us have a look what molecular orbital theory would have to say about the stability of the ferrocene molecule. So let us apply ligand field theory to the ferrocene complex in a way we have done it before. So we shall here assume D5H symmetry for the ferrocene, in which the pentagonal rings stand in eclipse form to each other. That is actually not realized on nature. Actually, we have a staggered form, but we will make this simplification in order to somewhat simplify our molecular orbital consideration a little bit, but the molecular orbital diagram that we'll construct will be insignificantly different from a molecular orbital diagram that you would get if you assume a staggered conformation. Therefore, the simplified version will serve the purpose of understanding the stability of the ferrocene ligand. All right, so now this eclipse form is associated with the point group D5H, and we need to assign our coordinate system in order to symmetry adapted linear combination of atomic orbitals. So a useful definition of the coordinate system would be if we said, well, that the z-axis would stand perpendicular to the cyclopentadienal rings here. The x-axis would point to the right, and basically the y-axis would point in the ball plane. Okay, so now we need to determine what are the symmetry types of the metal frontier orbitals. So the metal frontier orbitals of the iron will be 3d, 4s, and 4p, and we need to find these orbitals in the character table of the point group D5H. So s orbitals always have totally symmetric symmetry types. So the 4s orbital will have, in this case, A1 prime symmetry. So as far as the p orbitals go, you see the px and the py orbital. Here they are double degenerate and have the symmetry E1 prime. You see the z orbital here, the 4pz orbital here, it has the symmetry type A2 prime prime. You see the dz square orbital here for the symmetry type A1 prime. So the dx square minus y square and the dxy orbital, they are double degenerate and have the symmetry E2 prime. And the dxz and the dyz, they are also double degenerate and have the symmetry E1 prime prime. Okay, so this is just summarized here again. So now we need to be clear about our ligand orbitals and our ligand group orbitals. So now we will make the assumption that only the pi orbitals within the cyclopentadienal ligands interact with the metal d orbitals. Therefore, we only need to consider the pi orbitals in the molecular orbital diagram for the ligands. So, so the pi orbitals are being constructed by orbital overlap between the 2pz orbitals of the 5 carbons. So because we have 2 ligands, we have overall 2 times 5 is equal to 5 pz orbitals that we need to consider. 10 pz orbitals that we need to consider. Okay, so now see here the pi molecular orbitals of one pentacyclopentadienal ligand. All right, so we look perpendicular on this ligand, and all the orbitals that's shown here are the pz orbitals that stand perpendicular to the plane of this ligand. So we combine 5 2pz orbitals, so therefore we get 5 molecular orbitals per ligand. And you see here the most bonding one, which has no node. You see here 2 double degenerate ones that have 1 node. And you see here 2 other ones that have 2 nodes. So there's actually 1 node missing here for this one. So these 2 are interbonded. So now how many electrons do we have? So if we treat the cyclopentadienal ligand as a neutral ligand, then each pz orbital contains 1 electron. And we have overall 5 ligands to consider. If we treat it as an anionic ligand, there would be anion aromatic ligand, there would be 6. So here in this example, we treat it as a neutral ligand. So we have to fill the 2 electrons into this bonding molecular orbital, 2 electrons here in these weakly bonding molecular 3 orbitals, 3 electrons in these 2 weakly bonding molecular orbitals, and the 2 interbonding molecular orbitals remain empty. So now we have 2 of these ligands. Therefore, we have overall 10 ligand group orbitals to consider. So you see here what is called this so-called 0 node ligand group orbitals. And they are being produced through the interaction of these 0 node molecular orbitals with each other. So we combine them actually in 2 forms. Okay. So in one way, we have actually a bonding situation between the 2. Okay, so orbital lobes with same algebraic sign point toward each other. And this ligand group orbital has A1 prime symmetry. And of course, one could calculate this. And I'm omitting this step here. While here in this combination, orbital lobes of different algebraic sign point toward each other. So here we have an interbonding interaction, and the respective orbital has A2 prime symmetry. All right. Then in addition to that, we have the interaction between the 1 node orbitals to give 4 ligand group orbitals, as you can see here. So you see that we can have these two one-node molecular orbitals interact in two ways. So you see that in this way, we have a bonding interaction. While for this one here, we have an interbonding interaction. So this orbital here has E1 prime symmetry, and this orbital here has E2 prime symmetry. So we can also make the other one-node molecular orbital type interact. So you see here, again, the bonding interaction, and here the interbonding combination. So this orbital here would have E2 prime symmetry, and this one here would have E1 prime symmetry. You can also make the two-node LGOs interact, and again, for each of them, there's a bonding interaction, there's an interbonding interaction. So you create these four additional ligand group orbitals. You see here the bonding interactions for the first combination, here the interbonding interaction for the first orbital. So again, this orbital here has A1 prime symmetry. This one has A1 prime symmetry. So here you see the bonding interaction for the second two-node ligand molecular orbital. You see here that there's a bonding interactions. And here for this one, you have the interbonding interaction. So again, this one here has E1 prime symmetry, and this one has E1 prime symmetry. Okay, so now we have understood all our 10 molecular orbitals. Sorry, our 10 ligand group orbitals. And now in the next step, we must combine the CP ligand group also, which we have 10, with the iron frontier orbitals, which are our 4s, 4p, and 3d orbitals. And that will then give us the molecular orbital diagram for ferrocene. So let us do this. So we have here the metal frontier orbitals. You see here the symmetry types, which we previously determined. We have here the ligand group orbitals, okay, associated with their symmetry types. So these two here are the 0 nodes. These 4 here are the 1-node LGOs, and these 4 here are the 2-node LGOs. Okay, so now we can again make combinations of orbitals that have the same symmetry type. So for instance, we can start with the A1 prime symmetry type. So we have 1, 2, 3 orbitals to consider. That we will have 1, 2, 3 molecular orbitals. One is bonding, one is interbonding, and one is approximately non-bonding. All right. So next, for instance, we can look at the A2 prime molecular orbitals. So we have here this A2 prime, and we have here this A2 prime. So that gives a bonding, 1 A2 prime, and an interbonding 2 A2 prime. Okay. So next, for instance, we can look at the 1E prime. So you see you have these two 1E prime, and you have these two 1E prime. So that gives this bonding pair, and here the interbonding pair. Okay, so what else is left? We have the 1E prime left. You see that the 1E prime I have here for the 4p orbitals, and we have 1E prime here for the 1-node ligand group orbitals. So again, we get a bonding pair and an interbonding pair. So now what is left? We still have the one E2 prime. Okay, so we have here the E2 prime, this one here, and we have here these two E2 prime. So that gives this bonding pair, E2 prime, that's the one E2 prime, and this one here, that is the two E2 prime. Okay, what else? Well, we still have these E2 prime two node ligand group orbitals, but they do not find a partner, so they remain non-bonding. So now, what is left to do? Well, we still need to consider the electrons. So we say that we have, if you treat the ligand as a neutral ligand, 10 electrons, 5 times 2, that gives 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we see here, now we should treat it as an anionic one, which is which gives 12. We could do it either way, but in this example, we say we have 6 electrons per ligand, that gives 12. And then we treat our iron as an iron 2 plus. That gives here 8 electrons, but let's fill in these electrons first. So we have here these two, and that gives 4, 6, 8, 10, and 12. And you see that all these 12 electrons are in bonding molecular orbitals. So we have, therefore, here these orbitals here as the metal d orbitals in the ligand field, which is now a D5H symmetry. We could call it D5H ligand field. And all metal d electrons, which could be up to 10, would need to be filled into these 5 orbitals. Now, in this case, our iron has 6 electrons because it's an iron 2 plus. So if it was neutral, it was 8, but because 2 plus, we have 6 electrons. And these 6 electrons now need to go into these orbitals here. So now we see that we can fill all the bonding molecular orbitals. And this one here is more approximate non-bonding, but still the filling of these 2 electrons into this molecular orbital wouldn't be energetically very unfavorable. So overall, we would understand from the standpoint of the molecular orbital theory also why our ferrocene is a quite stable molecule. And again, the molecular orbital theory confirms the 18 electron rule. It says that, well, 18 electrons here in our molecular orbitals are most favorable. If we had less, we couldn't use this energetically relatively low molecular orbital. Here, if we had more, well, we would have to fill electrons into these strongly anti-bonding molecular orbitals. Okay, then let us stop at this point.